Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. This lecture is on Chapter 7, and we cover clouds, precipitation, and weather radar. So what do we want to talk about this chapter? First, how do clouds and precipitation form? And we find that clouds are products of condensation, or in the case of ice clouds, deposition within the atmosphere. Clouds are essential to the global water cycle, so without clouds there would be no precipitation. Yet most of the clouds do not yield precipitation. So in this lecture we'll cover the development and classifications of clouds and fog, the formation and types of precipitation, weather radar, and methods for measuring precipitation. So as you know, water vapor is invisible. But clouds are the visible products of condensation or deposition of water vapor within the atmosphere. As you near saturation, clouds are more likely to form. It's really hard to make clouds form in the laboratory. So for instance, remember we talked about physical models that are small scale models of a larger process. Well, it's really hard to get a cloud to form in the lab. If we do try to get clouds to form in the lab, what we actually have to do is make the air supersaturated. This is due to the curvature effect. So just as a simple model, let's consider our raindrop or our cloud pellets, or the things that make up the clouds, to be little spheres of water. And the smaller the sphere, the smaller the radius, and the greater the curvature. So the curvature of the water surface affects the ability of the water molecule to evaporate from the surface. If we have smaller the droplet, the greater the water vapor concentration needed for droplet growth. So this is what we mean. If we have a bunch of tiny droplets of water, what can happen is they can start clumping together and make bigger droplets. Well, if all the droplets are really tiny, then we need more of them so that they'll be closer together and they can form bigger droplets. So smaller droplets have greater radius of curvature than large droplets. They also have the fewest surrounding molecules, so they're more weakly bonded when they start to coalesce. And by coalesce we mean sticking together. Water vapor more readily escapes a curved surface than a flat surface, mainly because in a curved surface there's more surface area. Saturation vapor pressure is greater surrounding a small droplet versus a large one. So for water droplets with a radius of 0.001 micrometer, and micrometer is 10 to the minus 6 meters, saturation vapor pressure is up to 3.4 times greater than for larger surfaces. This equates to 340% relative humidity. For water droplets with a radius 1,000 times larger, so 1 micrometer, 1 micrometer, the relative humidity is only slightly higher than 100% is required. So now, what makes cloud formation possible? Well, if we look in the atmosphere, we talked about humidity, and what there are little water droplets, so water suspended in the atmosphere. If I want to make rain droplets, I need to take these small droplets of water and have them come together and make larger droplets. So as we said, outside the laboratory, if the relative humidity nears 100%, it's pretty easy to get clouds to form. And the reason is that suspended in the atmosphere, we have these solid or liquid particles known as nuclei, and they provide a relatively large surface area for condensation or deposition to occur. So what has happened is we have this water vapor, and then there's a little piece of solid something in the atmosphere, and water droplets will begin to stick to it or coalesce to it, and we'll get condensation on that solid particle. It can also be a liquid particle. If that particle is below 0 degrees Celsius, then when the water sticks to it, it will freeze and we get deposition. The nuclei have a radii greater than 1 micrometer. So it's larger than our largest water droplet. So when condensation starts on the surface of the nuclei, they become even bigger, and they can get together and collide with even more water molecules. These nuclei are essential for cloud formation. They're pretty abundant in the atmosphere. And the sources, of course, include volcanic eruptions, wind erosion of soil, forest fires, and ocean spray. Sea salt makes a really nice nuclei to get these clouds to form. And sea salt serves as a hygroscopic nuclei for cloud development. There's two types of nuclei. There's cloud condensation nuclei, which promote condensation at temperatures both above and below freezing. Some cloud droplets can remain liquid even at the temperature well below 0 degrees. We call these supercooled droplets. These are droplets of water that are still liquid even below 0 degrees C. We also have ice-forming nuclei, IN, and they promote ice crystal formation at temperatures well below freezing. So freezing nuclei, surfaces on which the water first condenses and then freezes. These are at active temperatures at about -9 degrees. Deposition nuclei are surfaces in which ice deposits directly from vapor. These are not active until temperatures below -20 degrees. The condensation nuclei are more common than the ice-forming nuclei. We also have hygroscopic nuclei, and these are a special case of the condensation-forming nuclei, and they have a chemical attraction for water. So clouds form more rapidly in their presence. A good example of a hygroscopic nuclei is magnesium chloride in ocean spray, and they can provide condensation at relative humidity as low as 70%. So living near the ocean, we know that we see a lot of clouds in the summertime, and a lot of this is formed by the salt spray that's blown up from the ocean surface. Cities can also spur clouds and precipitation development, and they do this by contributing water vapor, so they raise the relative humidity, and they add heat, which adds to the buoyancy of the air. If we want clouds to form, what we need is warm, moist air, or at the very least, moist air, to be brought up into the atmosphere. So it has to become buoyant and rise up through the atmosphere. So we see rainfall has been shown to be greater downwind from an urban industrial area, a city. We can also have supercooled water. Supercooling is fresh water cooled below its freezing point, but it still remains liquid. What happens here is that the droplets are so small that the actual kinetic energy prevents the growth of ice crystals. So when you think of ice, you think of a crystalline structure, but if these droplets are so small, it's hard for these crystals to form. So if you have little tiny water droplets, they can remain liquid even at temperatures below freezing. As the droplet temperature falls, the probability of an ice embryo growing to critical size increases because the average kinetic molecular activity decreases. So don't forget, we said temperature was a measure of the average kinetic energy of a molecule. We have homogeneous nucleation, and this is the formation of ice embryos of critical size due to the chance aggregation of water molecules. And if there's no foreign particles acting as ice nuclei, then cloud droplets can cool below -39 degrees C without freezing. The -39 degrees C is known as the Schaefer point. Additional cooling leads to homogeneous nucleation. By homogeneous, we mean that we're getting one form of droplets in the clouds, and in this case it'll be the ice embryos. Heterogeneous nucleation, we have supercooled water droplets, and they come in contact with foreign particles that are ice-forming nuclei. The cloud droplets will freeze at the temperature below freezing, but well above the Schaefer point. We can also see water molecules collect on the ice-forming nuclei and form an embryo that is close enough to critical size that additional growth causes the droplet to freeze. The clouds are classified based on their general appearance, the altitude of the cloud, the temperature, and the composition. So for appearance, we have the cirriform clouds that are wispy and fibrous. We have the stratiform clouds that are layered, and the cumuliform clouds that are heaped or puffy. For altitude of the cloud base, we have high, middle, or low, low being closer to the Earth. For temperature, we have a warm cloud, that's at about 0 degrees C, and a warm cloud that's at or below 0 degrees C. I'm sorry, we have a warm cloud that's greater than 0 degrees C, and a cold cloud that's at or below 0 degrees C. And we also have the composition that corresponds to temperature. So Table 7.1 shows a summary of cloud classification schemes. We have cold and warm clouds, and they can be composed of ice crystals, supercooled droplets or water droplets, and their altitude, we either have stratiform or cumuliform. And stratiform we have high, low, and middle. High, middle, and low. And cumuliforms are clouds with a lot of vertical development, so they could go through the low, middle, and high altitudes for a single cloud. Table 7.2 shows the cloud classification based on cloud groups and the altitude of the cloud base. And Table 7.3 shows some special characteristics of cloud type. So for example, you notice we have these anvil-shaped clouds, and these are cumulonimbus clouds. First we have high clouds, so first let's talk about high clouds. These have bases above 5 kilometers, and as we've said before, 5 kilometers is about 3 miles. The average temperature is below negative 25 degrees C or negative 13 degrees Fahrenheit. These clouds are composed almost exclusively as ice crystals, so they have like a fibrous appearance. And the names include the prefix cirro. So we have cirrus clouds that just look like wispy high altitude clouds, cirrostratus, and cirrocumulus. If we have a base between 2,000 and 5,000 meters, we have middle clouds. So this is roughly, let's say, 1.5 to 3 meters. Their temperatures are typically between 0 degrees C and negative 25 degrees C, or 32 degrees Fahrenheit and negative 13 degrees Fahrenheit. These are composed of either supercooled or they're composed of a composition between supercooled water droplets and or a mixture of water droplets and ice crystals. The names include the prefix alto. So altostratus looks like a hazy cloud that covers the whole sky, and altocumulus. Low clouds, we have based from the Earth's surface, so that's fog, up to 2,000 meters or 2 kilometers. Here the average temperature is typically between -5, is typically above -5 and 23 degrees Fahrenheit. These are composed mostly of water droplets, and they include stratocumulus, stratus, and nimbostratus. Usually only drizzle falls from stratus, but a significant amount of rain or snow may fall from the thicker nimbostratus. Cumulus clouds are visible on satellite images, and we can pick them up. When you're sky watching, you'll note that cumuliform and stratiform clouds are often observed in the sky together. You also might notice that different clouds move in a different direction, can move at different directions and speeds at different levels. So this is caused by something called wind shear. So the wind can change direction or speed as we move up through the atmosphere. And this becomes really important later, and we'll discuss it in detail when we start talking about forces. The strong vertical shear in horizontal wind speed or direction may cause the clouds to form something called cloud streets. You also might see holes that are formed by aircraft, so the turbulence may cause expansional cooling of supercooled water droplets. These droplets freeze to the ice crystals that fall out of the cloud. Here's some unusual clouds. So we have stationary disc-shaped clouds called altocumulus lenticularis, and these are generated when a prominent mountain range disturbs large-scale winds. And we start getting ripples in the flow, and what happens is as they move up, they're expanding and cooling and forming these clouds. We also can have mountain clouds. These are lenticular clouds situated over the mountain. And leeward clouds, these form on the leeward side of the mountain. If we have a stable atmosphere, so we have more dense cold air below and less dense warm air above, and the wind is blowing stronger in the less dense warm air, what we'll start to see is these ripples to form, just like you would see ocean waves form by strong winds blowing over the ocean. So the vertical shear in this horizontal winds creates Kelvin Helmholtz waves along this boundary. And we get these billow clouds are formed in their wave crests. We also have noctilucent clouds, and they form in the upper atmosphere above 80 kilometers, and they're seldom seen and only at high altitudes and at high latitudes. We also have fog, and fog is simply a cloud that strikes the ground, and it restricts visibility to about 1,000 meters or 1 kilometer or less. If you can see past 1 kilometer, then we call it light drizzle. So then it's a mist called light drizzle. But as soon as it restricts visibility to 1 kilometer, we call it fog. We also have different types. We have radiation fog. This is radiational cooling causes humid air near the ground to saturate. If you look, you can see the fog visible from these NOAA satellites. And they're showing here we see the fog in river valleys. And what we're seeing is advection fog. and the evecting air passes over a relatively cool surface and causes condensation to occur as the air cools. So we have warm, moist air, and it flows over the cool surface, and it cools and the water condenses. And this happens in the summer over the surface of the Great Lakes. We also have steam fog. This is also called Arctic smoke. And it develops in the fall or winter when extremely cold and dry air flows over a large, unfrozen body of water. So evaporation and sensible heating, don't forget sensible means a temperature change, causes the lower portion of the air mass to become more humid, and the warmer than the air above. At this point, the air is destabilized, and the consequent mixing of the mild, humid air with cold, dry air causes saturation and fog formation. And it looks like steam or smoke coming off the water. We have upslope fog. So if you've ever been up in the mountains in New York, you've seen this a lot. Right, the fog develops on the mountainside or the hillside, and what we have is ascending warm, humid air that reaches saturation. So it's the wind's blowing at the bottom of the mountain, it blows up humid air, which saturates as it starts to cool when it reaches the higher altitudes. Now let's talk about precipitation processes. Precipitation in water is water in solid or liquid form that falls from a cloud. It can reach terminal velocity, and this is what happens. Just like a skydiver jumping out of a plane, at first they begin to accelerate is at 9.8 meters per second squared. So about every meter, their speed increases 10 meters per second. As they begin to fall faster and faster, the air resistance gets larger. So the faster you're going, the more air resistance. So eventually, as the air resistance increases, you're still going faster and faster and faster towards the Earth, but the rate at which you're going faster begins to decrease. So at the beginning, each second, you're increasing your speed by 10 meters per second, but as air resistance starts to build up due to your speed increasing, you might only accelerate 9 meters per second each second, and then 8 meters per second each second. Eventually, the air resistance becomes so large that it equals the force of gravity, it equals the weight, at which case you hit terminal velocity. So you don't slow down, but you don't go any faster. Here shows the terminal velocity of some particles falling through the air with the size of the particle. So notice that as the diameter increases, we're getting larger and larger. For hail, we can hit up to about 10 centimeters. And the speed increases, the terminal velocity, and the terminal velocity is shown in centimeters per second. With ward cloud precipitation, we have a collision coalescence process. So the clouds are a bunch of water droplets. All of a sudden, a water droplet begins to fall. It collides into another water droplet and they stick together. Now they're bigger. They collide into two more water droplets and they get even bigger. And they get larger and larger, and eventually the droplets become large enough that their terminal velocity overcomes any updrafts that's trying to push it back into the cloud. And they fall as precipitation. So we have a tiny water droplet, it sticks together with another water droplet. It gets bigger and bigger, and eventually it reaches a size that it falls out of the cloud. If we have cold cloud precipitation, and a cold clouds or portion of clouds at temperature less than 0 degrees, these are mostly high and middle altitude or latitude clouds, and they form precipitation in an environment of supercooled water and ice crystals. At sub-freezing temperatures, these water molecules move readily and vaporize from a liquid water surface more than a water surface. At sub-freezing temperatures, water molecules more readily vaporize from a liquid water surface than an ice surface because water molecules have stronger bonds in the solid phase. So what we're saying is that if I have a body of water, even when it's cold out, it's easier to get those water molecules to vaporize than if it was a body of water covered with an ice sheet. Here this is something similar. Once again, we reach terminal velocity, and terminal velocity increases with increased ice crystal size. The larger crystals collide, and form larger ice crystals. And once again, they may fall out of the cloud base when they're large enough. And they may reach the Earth's surface either as snow or rain, depending on the ambient temperature below the cloud. So once falling, a raindrop or snowflake leaves the base of the cloud, and it enters in unsaturated air and begins to vaporize. Right, the amount of vapor, the amount that vaporizes increases with cloud base height. So, sometimes what you'll see is if we have a very high cloud and relatively unsaturated air below it, what can happen is the rain will start to fall, but before it ever reaches the ground, it vaporizes. These are known as virgus streaks of water and ice crystals falling from a cloud, and once again they mostly vaporize before they ever reach the Earth's surface. When we look at the precipitation that makes it to the Earth's surface, it can form in many forms. So we can have liquid, that's either rain or drizzle, freezing rain and freezing drizzle, or frozen. Right, so we have snow, snow pellets, snow grains, ice pellets, and hail. Rain has diameters of 0.5 millimeters to 6 millimeters, and they look like flattened spheres, not raindrop shaped like we always show them in cartoons. They're unstable at large diameters because what will happen is if you have a really large droplet of water, it'll break apart. And they fall mostly from nimbostratus and cumulonimbus clouds. Drizzle has diameters of 0.2 to 0.5 millimeters, and they originate mostly in stratus clouds and have limited growth by a collision coalescence process. We also have different forms of frozen precipitation. We have snow, and that can aggregate diameters can reach 5 to 10 centimeters. On the right shows some different um, forms of what the snow can look like. So we have snow pellets. They have diameters of 2 to 5 millimeters, and they're soft, conical or spherical white ice pellets or ice particles. And they form when super cold cloud droplets collide with an ice crystal and freeze. We have snow grains. These are flat or elongated, opaque white ice particles. And they form similar to drizzle, but they freeze prior to reaching the ground. We also have ice pellets that we call sleet. These are less than 5 millimeters. And they're spherical or irregularly shaped transparent or translucent ice crystals. They form when snowflakes partially or completely melt below an ice cloud base and then refreeze again. So this shows a graph of what you should see. If through the entire atmosphere we're below 0 degrees, we're going to end up with snow coming from the cloud. If we fall through an area that's 0 degrees, then reach an area that's warmer, so what will happen is the snow will melt, become rain, and then become sleet when it hits the Earth's surface. If that warm area is larger, what can happen is we'll have snowfall, turns to rain, and then it freezes once it hits the Earth's surface, so it'll freeze on things like trees and posts and the grass. And this is called freezing rain. And we can have the case that snow begins and then turns to rain as we move through this warm section of the atmosphere. So when we look at freezing rain, we have supercooled liquid precipitation that freezes totally or partially when it comes in contact with a frozen surface. So what we see here is the dew point and the air temperature. The air temperature is in red and the dew point is in green. And what you see is when it gets really close to the Earth's surface, the temperature has dropped below 0 and we'll get freezing rain. We also have hail. This is characterized by concentric onion-like layers of ice. They can develop within severe thunderstorms that are characterized by vigorous updrafts. And they need an abundance of supercooled water droplets. And it has to have a really large cloud vertical development. So what happens is updrafts inside the cloud lift ice pellets into the higher portion of the cloud, where they grow by collecting the supercooled droplets, and eventually they could exit the cloud. One thing we have to watch for sometimes is acid rain. So snow and rain are naturally slightly acidic, and they dissolve some of the atmospheric CO2, producing weak carbonic acid. So that's H2CO3. When the air is polluted with oxides of sulfur and oxides of nitrogen, we can also get acid rain to form. So these gases mix with the moisture and they form tiny droplets of sulfuric acid and nitric acid. So sulfuric acid is H2SO4 and nitric acid is HNO3. These acids dissolve in precipitation and may increase the acidity as much as 200 times. When we don't have any precipitation, what happens is sulfuric acid droplets can convert to acidic aerosols, and they can reduce visibility and may cause human health problems. So here we see a graph of the pH, and we have an acid is a hydrogen containing compound that releases hydrogen ions, H+, when it dissolves in water. An alkaline substance releases hydroxyl ions, and these are OH-. The acidity and alkalinity are expressed in terms of a pH, which is a measure of the hydrogen ion concentration. Rain with a pH less than 5.6 is considered acid rain. How do we predict when the rain is coming? We use the weather radar. And radar is an acronym for radio detection and ranging. So what happens is we send out microwave signals. They reflect off the cloud and come back. We know how fast they're going. We measure the time it takes for the signal to go, reflect off the cloud, and come back. And we can tell how far away they are. So for example, if you were moving 60 miles down the highway and you traveled for 2 hours, your car would have traveled 120 miles. So we can do the same thing, only this is at the speed of light. Also, don't forget, the time that we're measuring is the time for it to get to the cloud and come back. Therefore, if we want to figure out how far away it is, we use half of that time. So radar can predict dangerous weather and also can predict or can detect tornado circulation and the parent thunderstorm that causes the tornado. It can also monitor rain rates, so it reflects off the rain clouds. And they really came into their heyday back in World War II. In the 50s, Congress allocated funds to purchase long-range radar units for the purpose of detecting tornadoes and hurricane disasters. In 1959, coastal hurricane radars were established, stations were established. And in the 60s, they became common even in television weather reporting. In 74, there was a major upgrade. And in the 90s came the implementation of Doppler radar. Doppler radar uses something called the Doppler shift. So what these radars can do is not only detect how far away the storm is, but it can also detect whether the storm is moving towards us or away from us, and the speed at which it's doing so. So once again, we have a dish that looks like this. It sends out a pulse. It hits the rain. It echoes back. We measure the time it takes to get from when it leaves to when it comes back. We divide it by 2. We know how fast the microwaves were traveling, so we can figure out how far away they are. Here shows a dome for a radar. So we cover these with a dome to protect it from the rain and the elements. and the microwaves can get through the dome. This shows, the picture on the right shows a radar reflectivity product, and the echo's intensity is graduated by color. The Doppler shift works by using something called the Doppler effect. And if you take a course in physics, you'll learn that what happens when we have a source that's moving, if it's moving towards us, if it was making a sound, for instance, what we would hear is a higher frequency sound. And if it's moving away from us, we hear a lower frequency sound. So we can use this to figure out how fast the source is going, for instance, the storm, and in which direction it's traveling. Once again, we're using microwaves, not sound waves, to do this. But it's a little easier to think about sound waves than microwaves. So what happens is we send out the signal. It reflects off of the storm. It comes back. We can figure out how far it is by measuring the time. And if the frequency is higher than the frequency we set out, we know it's coming towards us. If it's lower than the frequency we set out, then it's moving away from us. So these are the Doppler images, and the greens and blues indicate motion directly towards the radar, where the reds and yellows indicate motion directly away from the radar. We can also use phased array radar, and this uses multiple beams set out simultaneously. They can scan the sky much faster and can focus on several weather features at the same time. We also want to measure precipitation, and rainfall and snowfall are routinely measured in terms of accumulation depth over a specified time interval, usually an hour, and every 6 hours and 24 hours. Measurements are made by gauges or remotely by weather radar or satellite sensors. So the standard non-recording rain gauge is just a cone with a big opening at the top, and that opening, we know what the cross-sectional area of that opening is, and we just measure the amount of rain that falls through that opening. We also have a weighing bucket. So what happens is these are calculated with the weight of rainfall in terms of depth. And what happens is the bucket fills, it drops, it moves a lever, and then empties out and then goes back to its initial position, fills up again. If we're measuring snow, what we have to do is melt that precipitation. So the tipping bucket rain gauge consists of a free swinging arm and a container and two compartments, each of which collects 0.01 inches or 1/100th of an inch of rainfall. And each compartment alternately fills with water, tips, and then spills its content. Weighing buckets rain gauge, they're calibrated for the weight of the accumulating rainfall. Snowfall measurements. Meteorologists are interested in the depth of the snow that falls over a certain region and the meltwater equivalent of the snow and the depth of the snow on the ground at the observed time. So new snowfall accumulates on a board placed on top of the old snow cover, and it's measured with a ruler. The meltwater equivalent can be determined by weighing bucket gauge measurements, or melting the snow in a non-recording gauge. As a very general rule, 10 centimeters of fresh snow melts to 1 centimeter of water. The actual ratio depends on the crystal form of the snowflake, so it depends on what type of snowflake you have. Of course, the depth of the snow on the ground is determined by an average of ruler measurements at several locations. So we just stick a ruler in and see how thick the snow layer is. We can also use remote sensing, so we can use radar reflectivity. And the reflectivity is proportional to the raindrop surface area, and the rainfall rate is proportional to the volume of the raindrops. So we can use radar to detect it. We can also use remote sensing of satellite. And here we have Tropical Rainfall Measuring Mission. We have a satellite that uses radar and a microwave imager and visible and IR scanners to estimate the rainfall. Okay, and that finishes today's lecture, and thank you for your time.